Hello, everyone. So, this is the start of a lecture series on foundations of representation learning and deep learning. In this series, we will build a clear and intuitive understanding of how modern AI systems actually work. We will begin from the basics, what a neuron does, and gradually move towards how representations are learned, leading into more advanced models and ideas. Along the way, we will also touch on important research concepts and papers to build deeper intuition. And toward the later part of the series, we'll explore directions the field is currently exploring, such as interpretability, world models, to understand what these systems are learning internally. The goal is simple, it's to make these concepts simple, connected, and intuitive. So today, in our first lecture, we will start with the simplest of all, a single neuron. And we will try to see how a neuron works from input to output. So let's get started. Okay, let's forget about neural networks for a second, right? And build everything from scratch. So let us draw this is our x-axis. This is our y-axis. So imagine we have some input and we want to produce an output, right? And we all are familiar with this equation. Okay, let me just write it this way. W x plus b. And this is the y equal to mx plus c equation, right? Linear equation, which we all are familiar with. Yeah. And you know what? This is the core of a neuron. This is core of a neuron. We see we are multiplying here and then we are adding here. That's it. So this X here and then this W here. What are these? This X here is input. And inputs bring us information. And then this W here represents the weights. They decide how important each part of the information is, right? How important each part of the information is. Importance. So basically, inputs carry the data and weights interpret the data. Now we were talking about this equation, right? This right here. Let's write it again for cleaner. This was our equation. Plus B. Now here Z is our signal. And what is signal here? You can see this is weight, this is input, right? So this is, we can say, is weighted evidence of a pattern. So when inputs and weights come together, we get this value Z, the signal. This is the signal. And this tells us how strongly the input matches what the neuron is looking for, right? Neuron is looking for a pattern. So let's go to this X and Y axis we drew here, and let's draw a straight line. Yeah, here we go. And this is our input, and this gives Z, that is output, right? So you see here, as the input is changing, the signal is also changing, right? Yes. Now this is negative and this is positive. So when we see negative, we have a weak signal. This thing here is negative and this is weak. We call it weak. And this part is positive and we call it strong signal. But also this weak signal over here, this does not mean that it's wrong. It just means it is not strong enough to matter. So the question here is, should the neuron respond to everything? I mean, all the signals, the weak and strong signal? Intuitively, no, it shouldn't. Some signals are just weak or noise, and some signals here actually carry some useful information. Useful info. So, our neuron needs a way to decide what matters, decide what matters and what does not. And I hope everyone is able to understand my writing. I'm sorry if not. I mean, please comment if you are not able to understand the writing. I'll try to improve in upcoming lectures. So yeah, where were we? Neuron needs a way to decide what matters and what doesn't. And then comes our activation function. Activation function. And there are a lot of activation functions. There is ReLU, which we will be talking about in here. There is sigmoid, etc. So this decision right here is made by activation function. So since we are talking about ReLU, let's go to ReLU. ReLU of x is maximum of 0 or x. So let's try to visualize ReLU function, shall we? Here you go, and here is this, and then this is x-axis, this is y-axis, this is 0, this is positive, this is negative, okay, this is positive, this is negative, and let's do this. Let's try to make it 0, and then it goes like this. So ReLU says, if the signal is negative, set it to 0. So here signal is negative, this part. So here we have a straight line, a line on x-axis, which is 0. Here signal is negative. And when signal is positive, let it pass, right? So here we see this is not 0. All the values here are non-zero, right? So basically, ReLU acts like a filter. It removes weak signals and keeps strong signals. So everything here gets ignored and everything here is passed, right? Let's, yeah. So since I said on the left hand side that was ignored, so it's 0 over here all along, and here it's non-zero all along. Now the neuron is making a decision. And what is that? So neuron is saying, is this signal strong enough for me to care? And activation function is helping neuron make that decision. So firing would take place here, and here it would be silent, the neuron. And here neuron would fire. So firing, that means we have it's active, and for silent, it's ignored. This is neuron firing we are talking about. So these neurons don't respond to everything. They only fire when something important is detected. So if we go and try to visualize the full pipeline, we have input, Then we had weight. Then we had signal. That was Z, right? This was W. This was X. This was Z. Then comes activation, which we discussed was ReLU here. And this gives output. So input brings in the information. Weights decide the importance. This brings information. This decides the importance. Signal measures how strong the match is. How strong the match is. Activation decides whether to respond. So in a way, we can say that this weight, it defines the pattern, and activation decides the response. Now let's see this. Linearity problem. Linearity problem. Let's suppose we have a lot of layers and all are linear. Linear plus linear, what it gives us? It gives us linear. Even stacking many layers gives us just a straight line. But real world patterns are not linear, right? It can be anything, but in real world, it's not straight line. It can be anything. It can be curved like this or like this or some XYZ function, some function, right? And activation functions for us. They introduce non-linearity. And this allows neural networks to model complex relationships. So far, we have looked at one neuron, but in reality, we have many neurons in a layer, right? So let's suppose we have here layer 1, and we have neurons. And then we have layer 2, we have more neurons. Then this goes like this. So each neuron produces an output, and that output becomes an input to the next layer, this layer. So outputs from one layer become inputs to the next. Outputs from one layer is input to next layer. And here's something important. All neurons in a layer work at the same time, this entire thing. They work at the same time. So we can say, and then simultaneously inputs from every neuron from layer 1, outputs from every neuron from layer 1 is input to neurons of next layer. So what we can say is, within a layer, it's parallel, and across layers, it is sequential, right? So neural networks don't become powerful because they are deep. They become powerful because they are non-linear, right? So far we covered input and weights, and then signal, weak signal, strong signal. We covered activation function, in which we saw ReLU. We discussed about neuron firing, non-linearity, multiple neurons, and the layer flow. Now the next question would be, how does the neuron learn the right weights? This would be our next question. And that would be in lecture 2. I hope I'll also release lecture 2 soon. So yeah, I hope this entire thing was helpful for you all, and happy learning. Thank you.